Over the last half-century, computing hardware has scaled at a rate unmatched by any physical industry. Processors went from holding a few thousand transistors to tens of billions, shrinking down to the nanometer level while exploding in raw processing power. In 1965, Gordon Moore observed that the number of transistors on a microchip doubled roughly every 2 years, while the cost plummeted. This observation, Moore's law, became the relentless metronome driving the entire technology sector. This chart shows the historical progress of the computing industry. The steep exponential curve is hardware capability. But look at this second, nearly flat line at the bottom. That tracks the daily production-ready output of an individual software developer. We have faster machines. We have high-level programming languages that compile in milliseconds. Yet the amount of debugged functional code a single engineer writes on an average Tuesday is nearly identical to what it was in the 1970s. The gap between these two lines continues to widen. Hardware scales automatically with physics and manufacturing. Software, on the other hand, remains a manual, error-prone human bottleneck. Shrinking a transistor is a physical engineering problem, and we solved it. Building software is a problem of a completely different class, one that actively defies Moore's law. Faced with this massive bottleneck, the tech industry reacts the way it usually does, by hunting for a shortcut. They're looking for a silver bullet, a single technology, a new management framework, or a novel programming language that promises an order of magnitude leap, a 10 times multiplier in developer output. Every few years, a new paradigm is pitched: object-oriented programming, or agile methodologies, and low-code platforms. Each is marketed with the promise that this specific tool will finally clear the backlog and automate the friction of coding. Computer scientist Fred Brooks argued decades ago that this endless hunt is doomed. It fails because it misdiagnoses the actual nature of computer software. We are not constrained by the quality of our text editors or compilers. We are constrained by the inescapable complexity of the real-world problems we are trying to model. To understand why coding remains so slow, Brooks proposed a mental model that divides software design into two distinct categories of complexity. The first is accidental complexity. This is the friction introduced by our own inadequate tools. It includes tasks like manual memory management, configuring server environments, or fighting with a language's obscure syntax. It is tedious, but it is a byproduct of the computing environment, not the problem itself. This translucent shell is accidental friction. Beneath lies a dense core, essential complexity. It represents the strict business logic required to solve a problem. Unlike nature, software engineers model human systems, tax codes, air traffic control. These are inherently arbitrary, messy, and highly complex. New languages and frameworks are excellent at stripping away the accidental friction in that outer shell, but they cannot abstract away the essential logic required to map a messy reality into executable code. Let's assume a revolutionary tool enters the market, and it is flawless. What happens to our developers' output if this tool eliminates all accidental complexity? Watch this tool strip away the outer shell. The massive, essential core remains untouched. If accidental friction is 10% of the workload, the tool yields only a 10% gain. The remaining 90% is core logic. 1,000% leap is mathematically impossible. The marketing hype surrounding the next big framework routinely claims order of magnitude improvements, but those claims contradict the theoretical limits of what any tool can achieve. The silver bullet cannot exist. Realizing tools won't give a 10 times speed up, management tries to bypass the ceiling by brute force, throwing more bodies at the project. This instinct leads directly to what is known as the Mongolian horde approach to engineering. It is famously addressed by Brooks' law. Adding manpower to a late software project only makes it later. Software isn't a manufacturing line where 10 workers build 10 cars. Scale the team and required communication paths explode combinatorially. 3 developers have 3 lines of communication. 10 developers have 45. Each new hire drastically increases the friction of keeping everyone aligned. Existing developers must stop writing code to train the newcomers. More critically, as the team fractures, the software loses its cohesive architectural vision, leading to conflicting code and compounded errors. A functional system requires intense conceptual integrity. Human communication overhead creates a hard limit on how fast any team can scale, trapping management in a paradox where spending more money slows the project down. Today, engineers are tasked with building open-world software, systems that must adapt to constantly emergent requirements and seamlessly connect with hundreds of other external applications. Technology executive Max Hopper described this environment as a relentless technology treadmill. Engineers must continually learn new protocols, updated languages, and changing security standards just to maintain baseline functionality. Adopting these evolving tools is mandatory for corporate survival. But organizations err when they mistake these necessary updates for shortcuts that will eliminate their underlying essential complexity. The modern engineer is forced to run faster just to stay in place. They face a landscape that demands continuous adaptation, with no promise of a magical productivity solution. If there is no silver bullet and scaling human teams fails, how do we actually manage essential complexity? The most effective strategy is the buy, don't build philosophy. The only reliable way to bypass essential complexity is to reuse logic and component architectures that someone else has already built, tested, and verified. You don't write what you can acquire. When custom code is unavoidable, success relies on strict adherence to two principles: the separation of concerns and effective modularity. A massive system must be divided into distinct, isolated modules that can be solved and tested independently. This is the only proven defense against a codebase collapsing under its own weight. True progress in software development doesn't come from a new framework. It comes from abandoning the search for marketing magic and committing to the rigorous, unglamorous discipline of first principles engineering design.